It's Thursday, the 4th of April. I've just got through reading the preliminary report from the Ethiopian Airlines flight number 302 that was lost on the 10th of March in Ethiopia. I'm a commercial pilot with a major airline here in the United States. Been doing that for about 20 years, been flying total for about 40 years. And this report, reading it, is absolutely gut-wrenching because this crew came so close to saving this aircraft, and at the same time, the MCAS system in the new 737-8-9 MAX aircraft, this report shows how overwhelmingly powerful this system can be in its original design configuration. My name's Juan Brown. We're going to go through this report step by step. I'm going to explain highlights along the way. This requires a certain level of understanding of the MCAS system, which we've reviewed in previous videos, and I will add an addendum at the end of this video, a review of the MCAS system. Remember, the MCAS, Maneuvering Characteristics Augmentation System on the new 737-8-9 MAX Boeing aircraft, is designed to assist a pilot in the event of a stall. If it senses a stalled condition via the AOA indicators, it will apply automatically. If the flaps are retracted and the autopilot is off, the MCAS system will apply about 9 seconds of trim, about 2.5 units of trim. It will then pause for 5 seconds, and if the MCAS system still indicates a stalled condition with the aircraft, it will repeat that process. Again, about 9 seconds of nose-down trim, achieving about 2.5 units of nose-down trim. The MCAS system, as originally designed, will continue to do this until you will reach the full nose-down extent of the stabilizer trim system. Flight departs Addis Ababa at about 05:38 Zulu time. These times are all in Zulu time. The entire flight only lasts a little over 6 minutes, so we'll be measuring time in minutes and seconds, starting with 5:38 as the takeoff time. Flap settings at 5 degrees, stabilizer trim setting to 5.6 units. That's normal. During the takeoff roll, the engine stabilized at 94% N1. That's a normal takeoff power setting for that elevation of airport at that temperature. The N1 reference remained about 94%, and the throttles did not move throughout the entire flight. Again, at that high takeoff power setting, if you are in level flight, you're going to achieve a very high rate of indicated airspeed very quickly. At 9:38:44, so this is only 44 seconds later, shortly after liftoff, the left and right recorded AOA values deviated. The left AOA, angle of attack, this is the little angle of attack indicator on the left side, captain side of the aircraft. The angle of attack sensor, I should clarify, located right here, decreased to 11.1, then increased to 35.7 degrees. These are huge fluctuations. While value of the right angle of attack indicator indicated 14.94 degrees, or about 15 degrees. Then after, the left AOA value reached 74.5 degrees in 3/4 of a second, while the right AOA reached a maximum of 15.3. So clearly, the right AOA is operating normally. Something's going on with the left angle of attack indicator. We don't know if it's the vane itself or if it's the electronic output from the vane. Also, airspeed, altitude, and flight director pitch bars value from the left side noted deviating from their corresponding right side values. So right away, we're starting to get instrument indications that are misleading. I'm going to leave out some of the steps of this report just to get through it quickly here, because some of this is a normal departure procedure. At 05:39, just a minute later, the captain calls out command. He's trying to engage the autopilot. Between liftoff and 1,000 feet above ground level, the pitch trim position moved from 4.9 to 5.9 units in response to manual electric trim input. At 1,000 feet, the pitch trim position was 5.6 units. That's normal. At 3922 and at about 1,000 feet, the left autopilot was engaged. You don't typically want to engage the autopilot. You have a left and right autopilot. You typically don't want to engage the autopilot for the affected side to the on position. If you can determine which side at this point is giving you bad information. It disengages about 33 seconds later. At 39:45, a minute and 45 seconds, captain requests flaps up and the first officer acknowledges. 1 second later, the flap handle is moved and the flap retraction begins. Remember, MCAS only actuates when the flaps are retracted and the autopilot is off. At 05:39:55, a minute and 55 seconds after takeoff, the autopilot disengaged. It doesn't say whether the pilots disengaged it or if it was kicked off automatically.
An autopilot will kick off automatically anytime it senses a grossly out of trim condition.
At 39:57, the captain advised the first officer to request to maintain runway heading because they're having flight control problems. Typically in an emergency, you're trained to maintain runway heading and deal with the problem. That's normal in the event of an emergency. At 05:40, 2 minutes now after takeoff, shortly after the autopilot disengaged, the flight data recorder recorded an automatic aircraft nose down activation for 9.0 seconds, and the pitch trim moved from 4.6 units to 2.1 units. The climb was arrested and the aircraft descended only slightly. Remember the specifications for the MCAS system? It would move automatically 9 seconds worth of nose down trim movement, yielding about 2 units of nose down change. At this time, they begin to start getting their first of a series of ground prox warning systems. Don't sink, don't sink. It's an automatic call out based off of the radar altimeter and the rate of climb of the aircraft, or the lack of rate of climb of the aircraft. The column moved aft and positive climb was reestablished during the automatic nose down trim motion. Approximately 3 seconds after the automatic nose down stabilizer motion ends, the electric trim from the pilot activated switches on the yoke are moved in the aircraft nose up direction and stabilize the trim at about 2.4 units. The aircraft pitch attitude remained about the same as back pressure on the column increased. So here's presumably the captain beginning the fight with the MCAS system by manually counteracting it with the electric trim on the yoke in the nose up direction. Approximately 5 seconds after the end of the nose up stabilizer motion, a second instance of automatic nose down stabilizer trim occurred, and the stabilizer moved down and reached 0.4 units. Again, this is clearly input from the MCAS system. Ground prox warning system is going off. Don't sink, don't sink. The captain advised the first officer to trim up, nose up with him, so they're still trying to fight the system using the electric trim. Manual electric trim in the nose up direction was recorded, and the stab trim recovered at 2.3 units. At 05:40:35, so that's 2.5 minutes after takeoff, the first officer, this is the guy with only 200 hours, makes the right call and calls stabilizer trim cutout 2 times. The captain agrees, and the first officer confirmed the stabilizer trim cutout. So they've done the correct procedure here 2.5 minutes after takeoff, wrestling with this thing, and they've cut out the stab trim cutout switches. Approximately 5 seconds after the end of the nose-up stabilizer motion, a third instance of nose-down automatic trim command occurred without any corresponding motion of the stabilizer, which is consistent with the stabilizer trim cutout switches in the cutout position. In other words, MCAS is trying to shove the nose down of the aircraft, but they've hit the cutout switches, so it is having no further effect on the trim of the aircraft. The crew continues to struggle with the aircraft, and from 5:42 to 5:43:11, for a period of about 2.5 minutes, the stabilizer position gradually moved in the nose down direction from 2.3 units to 2.1 units. Now, I'm not clear what could have caused that. There are a couple other systems on the 737, like elevator feel and mock trim, that may be at work behind the scenes even with the stabilizer trim cutout switches in the cutout position. Or did the crew misapply manual trim? It's not clear why this would have moved just a little bit towards the nose down direction. All this time, those throttles are still up at 94%, and now indicated airspeed is increasing from 305 knots to 340 knots. They're at red line, they're at VMO now. And there was a little discrepancy between those airspeed indicators. At high airspeeds, any out of trim situation is going to be highly exacerbated. At 05:41:20, the right overspeed clacker was recorded on the CVR and remained active until the end of the recording. The clacker is the indication that you are exceeding red line airspeed of the aircraft. You're simply going too fast. The crew continues to attempt to work together to pull the nose up. The left overspeed warning is activated at 41:32 and active all the way to the end of the recording. At 41:46, now about over 4.5 minutes into this thing, the captain asked the first officer if the trim was functional. The first officer has replied that the trim was not working and asked if he could try it manually. The crew is just now getting around to attempting to manually trim the aircraft at redline airspeed close to the ground. The captain told him to try. At 05:41:54, the first officer replied that it is not working. In other words, the manual trim is not working. I'll explain in a minute why the manual trim would be so difficult to operate in this situation. Crew discusses a couple more warnings that illuminate, including left alpha vane. The captain asked the first officer to pitch up together and said the pitch is not enough. Now at 05:43:11, 5 minutes after departure and approximately 32 seconds before the end of the recording, at about 13,400 feet MSL, still very close to the ground, within a couple thousand feet of the ground or less, 2 momentary manual electric trim inputs are recorded in the airplane nose-up direction. The stabilizer moved in the nose-up direction from 2.1 units to 2.3 units. About 9 seconds later, approximately 5 seconds after the last manual electric trim input, an aircraft nose down automatic trim command occurred and the stabilizer moved in the nose down direction from 2.3 units to 1.0 unit in approximately 5 seconds. The aircraft began pitching nose down. Additional simultaneous aft column force was applied. but the nose down pitch continues, eventually reaching 40 degrees nose down. The stabilizer position varied between 1.1 and 0.8 units for the remainder of the recording. The left indicated airspeed increased, eventually reaching 458 knots. The right indicated reached 500 knots at the end of the recording. There's only one explanation for this last couple of paragraphs here in this report, and it's not explained. But the only way that you can apply electric trim inputs, and the only way that the MCAS can once again take over control of the aircraft, is if one of the crew members put the stabilizer trim cutout switches back into the operational position. The runaway trim procedure and the MCAS procedure clearly states that to turn the stabilizer trim cutout switches to the cutout position and to leave them in the cutout position for the remainder of the flight. However, remember, the captain reserves the right to do what he deems necessary to overcome an emergency.
But this decision to return the stabilizer trim cutout switches back to the operational position, if found to be true, may have sealed this crew's fate.
Now let's talk about why the manual trim would be so hard, so difficult to trim in this particular situation. If this is your jack screw, and this is the nut that turns on the jack screw that raises and lowers the leading edge of the stabilizer, in an out of trim, grossly out of trim condition, the leading edge of the stabilizer is in the nearly full nose up position and has a tremendous amount of force on it as you're trying to pull back on the elevator in the tension direction. If you are trying to manually trim the aircraft, you're trying to rotate this nut against all the tension that is being applied to the stabilizer and the entire trim system. With the manual trim wheels alongside the pedestal of the 737, that force may exceed the capability of the trim wheels, especially at such high air speeds and so close to the ground in such dense air. Years ago, this was demonstrated to us in the simulator. Typically, how this setup would be is the instructor in the left seat would distract you with some instruction outside of the demonstration that he's about to show you, and while he's got you distracted, he would casually put some nose down trim into the aircraft. The trim wheels would turn, but you wouldn't notice it because they turn frequently in the 737. The instructor would get the aircraft in a fairly out of trim position in the nose down trim position, but he'd be holding the nose level by applying back pressure to the yoke. He would then ask you to take the aircraft and hand the aircraft over to you in this grossly out of trim condition, and you would be absolutely startled and surprised again about how far out of trim this aircraft was, as it took considerable force to catch the nose and hold it up there, forcing you to apply the runaway trim procedure and hit the stab trim cutout switches. Now the instructor would demonstrate to you how difficult it is to manually trim the aircraft at high speeds when it's severely out of trim. And he would ask you to try to trim the aircraft, and you could feel just how stiff that trim manually would be trying to overcome the forces on the jack screw with a severely out of trim aircraft. He would then demonstrate to you that you could relieve some of that pressure if you allowed the nose to drop and take some of that pressure off the jack screw. So you'd ease up on the back pressure, you'd allow the nose of the aircraft to come down, and then grab that trim wheel and start turning it. And unloaded, it would start to trim quite easily. You apply that back pressure to hold the nose up and keep it up, you'd find that mechanism would start binding up again, and it would be very hard to manually trim the aircraft. This is what the crew of the Ethiopian flight faced. And they did not have the luxury of altitude in order to help them unload the aircraft. These accidents with the 737 MAX series of aircraft will have large ramifications throughout the airline industry. I'll keep you posted here as we get further updates onto this situation, and we'll be answering your many questions from the comment section below in further updates. So stay tuned and see you here. Here's a quick systems review of the MCAS from my previous update. What we're learning about MCAS is that the primary input to the computers is the angle of attack indicators located on the side of the aircraft. But it does not take input from both angle of attack indicators. It unfortunately, as presently designed, only requires input from one single angle of attack indicator. Again, the angle of attack indicator is mounted on the side of the aircraft and gives you the reading of the critical angle of attack on the wing very accurately. However, if that one angle of attack indicator is malfunctioning or giving wrong information to the flight control computer system or the MCAS system may sense that the aircraft is in a stalled condition when it in fact is not.
The angle of attack vanes are located here on the 737 MAX. These AOA vanes are delicately balanced and robustly heated against airframe icing. The AOA vanes measure the relative wind and its angle of reference to the critical angle of attack of the wing. The AOA vanes are all part of the pedostatic system and are fed into the air data inertial reference units. Note there are two of everything for redundancy. The air data inertial reference units are then fed into the flight control computer, and along with the pilot controls, assisted by the hydraulic system, this information is fed through two more computers and the new MCAS system before delivering a signal to the stabilizer trim, which is controlled by a jack screw mounted on the leading edge of the horizontal stabilizer. Raising the jack screw or the leading edge of the horizontal stabilizer produces nose down trim. And the only way to completely shut this system down is with the stabilizer trim cutout switches located on the forward pedestal.
Other things we're learning about the MCAS system: it is apparently only operational when the flaps are up, it's retracted, and the autopilot is off. As far as the power of the MCAS system is concerned, anytime the pilot interrupts the MCAS system by trimming the aircraft in the opposite direction, that resets the MCAS system. As soon as you release your trim input, the MCAS system, if it's sensing a stalled condition, will continue to drive the stabilizer trim jack screw, or the stabilizer trim itself, further nose down if it's still sensing a stalled condition. And this struggle will continue between the pilot putting in manual trim inputs and the MCAS driving the nose down, and is capable, the MCAS system, as presently designed, is capable of driving the stabilizer nose down trim to the full nose down position.
A situation which is virtually unrecoverable at high rates of speed close to the ground.